Okay, let's see if I can do this problem. Okay, all right, so on the potential energy curve, you're still going to sort of have your initial, right, your energy initial equals energy final. And you're still going to use 1/2 mv squared or whatever, but you're going to have this potential energy function instead of mgh, okay, or kx squared, okay, instead of mgh or kx squared or 1/2 kx squared, but the rest of it is all like the same thing, okay? All right. Okay, so a particle of mass 4 kilograms is constrained to move along the x-axis under a single force where Fx equals negative cx cubed, where c is 8 newtons per meter cubed. Okay, the particle speed at A, all right, so we have 0, we have xa is 1 meter, and it's going 6 meters per second there, okay, and then it's going to go, oops, that was kind of a bad drawing. I didn't expect it to go that way. XB is going to be negative 2 meters, and that's where we're trying to find the speed. Okay? All right, so basically here's what we have, right? So we have something that's here, okay, and it's moving with a positive speed, okay, and it's acting under a negative force, right? So it's probably going to slow down as it moves this way and then speed up and come back to 2 meters. Okay, kind of like rolling up and down a hill, right? With the force being negative, right, which would be just like a downward hill force, okay? All right, so the first thing that we have to do is we know that the force function is negative cx cubed, okay? And we know that the force is the negative derivative of the potential energy graph, okay? All right, so that if I want to take the, if I want to find that, I have to do the negative integral of the force function dx, right? I hope I'm writing this right. You calculus people can tell me. Okay? All right, so if I do that, then I have negative cx cubed dx. Okay, and so then if I integrate that, that's going to turn positive, right? Because a negative force would mean a positive potential energy. Okay, so if I move that 3 down there, I'm going to have c over 4, oops, x to the 4th, right? So if you don't really know how to integrate yet, right, just think about putting something that if you took the derivative, it would be the line above, okay? And then I don't really need to evaluate that because I'm just going to keep it in terms of x for whatever potential energy function that I need, okay? All right, since c is 8, right, so that's going to be 2x to the 4th is my potential energy function, okay? Right, then all I really need to do, I'm going to totally run out of space, is at point A, right, I have like the kinetic energy at A plus u of x at A equals the kinetic energy of B plus u of x at B. All right. And then I can solve it in any number of ways, but this is not how I did it before. But okay, so 1/2 4 kilograms 6 squared, okay, plus 2, and then x to the 4th is 1, right, equals 1/2 4 v squared, that's what I want, plus 2, and that's going to be evaluated at negative 2 to the 4th, okay? I hope I get the same answer as last year. We're going to see. All right. Okay, so I'm going to have 0.5 times, oh my God, 0.5 times 4 times 36. So I'm going to have 72 joules there plus 2 joules equals 2v squared plus, what's negative 2 to the 4th? 16, 32 joules. Okay. All right, so I'm going to have over here 74 minus 32. I'm going to have 42 joules equals 2v squared. Okay, so v squared equals 21, or v equals radical 21 is 4.6 meters per second. Okay, so it's just kind of like a regular simple energy problem, but first you have to take the integral of the force function to get to the potential energy function.